Hi, my name is Bischoff from the University of Cincinnati. I'm here on behalf of the BICEP Collaboration to tell you about our ongoing observational effort at the South Pole, including the BICEP 3 telescope, which you see here in the foreground, and the BICEP Array telescope located in the Mapo building, which you can see in the background. I'll start by telling you a little bit about the science that we're trying to accomplish. This is a cartoon view of the history of our universe. We're here at the far right-hand side in the modern universe, which is full of interesting structure like stars and galaxies. As we look out into space, we're also looking back in time. And the furthest back we can look is to this very special epoch here that's labeled the cosmic microwave background. This is when the universe was at a temperature of about 3000 Kelvin. The redshift was about 1100. And this was the time when the hydrogen in the universe transformed from an ionized plasma to neutral atoms. So before this time, with the universe fully ionized, it was also opaque, and that means we're not able to see any further. So if we want to understand what was going on at the time of the Big Bang, we can't see that directly. Fortunately, the cosmic microwave background gives us tools to study that time. And the way we can do this is by looking at a snapshot of the state of either density waves or potentially gravitational waves that are generated early on in the universe, but leave an imprint on the microwave background that we can observe today. So in particular, we're really interested in trying to measure the signature of these gravitational waves, which are a holy grail in cosmology, because these would be the most direct probe of this theory called inflation, which was proposed to account for the apparently finely tuned initial conditions of our universe. You can see here that both these density waves and the gravitational waves are going to imprint signals on the polarization of the cosmic microwave background. That polarization can be geometrically decomposed into two parts: an E-mode polarization pattern that is sourced by both density waves and gravitational waves, if those exist, but also a B-mode polarization pattern, and that is going to be really the unique signature of gravitational waves. So that's what we are searching for with the BICEP telescopes, is this B-mode pattern in the polarization of the cosmic microwave background. We've been doing this for about 14 years now and have developed a really successful strategy in searching for primordial B-mode polarization. This strategy has four main components. First, we need very high sensitivity measurements. We achieve this with background limited transition edge sensor detectors, building telescopes with very high optical throughput, and relentlessly observing the same small field of sky from the South Pole. It's also really important that we have exquisite control of instrumental systematics. Some of that is done through the experiment design. Some of it is done through characterization and calibration measurements, which will be discussed in Brody Elwood's talk up next, and then also through our data analysis. We need to separate the cosmic microwave background signal that we're interested in from foregrounds due to our Milky Way galaxy. And that we can achieve with multi-frequency observation, particularly with the Keck Array and BICEP Array instruments that had multiple telescopes, each observing at different frequencies. And then finally, we're going to need to separate primordial B-modes from a secondary B-mode signal due to gravitational lensing, and that we are currently working on in collaboration with the South Pole Telescope. We've made observations over many years with an evolving set of instruments. Currently operating now is BICEP 3 and also the BICEP Array. And the key parts of this evolution is, first of all, we've added more and more detectors, which has increased the raw sensitivity of our experiment. And we've also expanded into more and more frequency bands, which is represented by the different colors of the focal planes down in the bottom row. And that we use for separating the galactic foregrounds from the cosmic microwave background. This image shows our both the achieved sensitivity in terms of the noise in our maps, but also in our sensitivity to the tensor to scalar ratio, R, which is basically parametrizing the amplitude of these gravitational waves. The X's indicate published results, And then beyond that is our forecasted results. We hope by the end of 2027 to reach a 1 sigma error on R of 2 times 10 to the minus 3 to 3 times 10 to the minus 3. But it's going to be essential to de-lens our data with the assistance of South Pole Telescope in order to reach that potential. Thank you very much.